This product, you give it a new name, you call A star. Alright? X is still here. And this product, you call it B star. You understand? This is a little bit different from this way. It's a little bit different. Right? Now, suppose A is symmetric. A is symmetric. What do you say about A star? Is that symmetric or unsymmetric? Do you understand my question? The matrix A is symmetric to start with. If you pre-multiply with P inverse, the product here, P inverse is a new matrix. So my question I ask you is, will this one symmetric or unsymmetric? It will be unsymmetric in general. Because when you have a symmetrical matrix, you multiply with some general inverse of the matrix, the product generally will be unsymmetric. Do you understand? So what does that mean? That means if you have the matrix A symmetric to start with, that approach is better. Because that approach will make sure that A star remain to be symmetric. Do you agree? But in this approach, the matrix A star will no longer be symmetric. It's not good. So this method is not good. Can you tell me in what situation that this method is good? Do you understand my question? If the matrix A is symmetric, then this method is not good. You agree? Because it will destroy the symmetry property. You agree? So can you give me an example in what situation that this is a good way to do? Well, if your matrix A from the beginning is unsymmetric, if your matrix A is unsymmetric, it becomes unsymmetric, you have nothing to lose. Right? Do you understand? So, you have two situations. If the matrix A to start with is symmetrical, then use this way to transform. If the matrix A is unsymmetrical to start with, then this way is a good way because it is simpler. Do you understand? Alright. Now, no matter which way, the next thing I want to discuss with you is how to find the matrix P. In America, we make a joke, we say that is a $6 million question. That means it's so important. Okay, here's the criteria. I said to you, matrix, this is a precondition, matrix P must be, there are two criteria that you need to know in order to set up this guy P. Must be what? Must be what? Number one, is how to find out the precondition matrix P inverse. Because we're talking about P inverse here. Okay, must be P inverse must be A is close to A inverse is possible. That's the first criteria. Whatever the matrix P that you want to figure out, right, you want to find, it should be inverse, should be as close to A inverse as possible. Which means what? The matrix P should be as close to A as possible. Do you understand? That's the first criteria. The second criteria is P inverse must be cheap to obtain. Must be cheap to obtain. So you have two criteria. Now here's the bad news. These two criteria are in conflict to each other. In other words, if you say, so the first criteria to provide the so-called good quality. The first criteria, it will give you the good quality. Meaning what? Meaning it will make sure that the new matrix A star will have a good condition number. It will guarantee that good quality. And the second criteria says it is cheap to obtain. Now, based on my previous lecture, remember we talked about Cholesky factorization? Suppose this is a good question I want to ask you. Suppose I give you this problem. A matrix A times a matrix B times a matrix C inverse times a vector D. Now, suppose I give you the matrix A, I give to you. Square matrix, I give it to you. I give you a matrix B, I give it to you. Matrix C is also given to you. And the vector D is also given to you. Okay, I give you everything, right? Now I ask you, I want to compute A times B times C inverse times D equal to what? Now, of course, in theory, you can do it, right? Because I give you A, B, C, you can find out inverse, you can time, blah, 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 you can figure it out, all right? But here's a tricky question. What is the order of computation? Do you understand? Should you do this one first? Let's say first. Then after that, you find out the inverse of C. That means you do this one, let's say, second. Then after that, you do from here to here. You do it third. And then finally, you do from here to here. You do it fourth. Is that a good order? Or that is a stupid order, in your opinion? Do you understand my question, right? Of course. You can multiply these two in the first, then the result of that, and then you try to find the inverse, and then you combine the result, and then finally take the matrix times D. That will give you the correct answer. But is it a good or the stupid way to do? Very stupid. I tell you two reasons for why it's stupid. The first thing is, I ask you, when you multiply two matrices, does it cost you more or does it cost you less compared to multiply a matrix with a vector? Well, let me give you even easier. Let's forget about the inverse for now. Forget about the inverse for now. Huh? Forget about the inverse. You take these two, right? And then the result, you times this guy. And then finally, you times D. If you do like this, what does that mean? This is matrix times matrix. You agree? Matrix times matrix. So you have one matrix times matrix. You agree? Then the result of that, you times C. That will be another matrix times matrix. So that will be plus another matrix times matrix. And then the result of that, you times D. That will be plus what? A matrix times a vector. Do you agree? Yes. So if you do this way, that means you need to have two matrix times matrix operation plus one matrix times vector. Now, of course, you know matrix times vector is a lot cheaper than matrix times matrix. Do you agree? Yes. Right? So based on that, can somebody here suggest me what is a good order to do? Any suggestion?
First, we can calculate a product C times D.
Of course, you understand. That's right. Of course, you do C times D. That will be matrix times vector. That's the first thing. Then after that, you will do this
Yeah.
and that. That will be another matrix times vector.
Yeah.
So that's 2. And then you do like this, 3 matrix times vector. That costs a lot less than the other way. Okay? Now, next question is a little bit more tricky. And let me test you. Make sure you understand so that I will help understand. Suppose A, B times C inverse. I give you A, I give you matrix B, I give you the matrix C. I give you the vector D. I want you to compute this one. Now, of course, based on your idea, perhaps you will say, the first thing I will try to do this one first. You agree? Don't worry about the detail for now. For example, you want to do some kind of inverse times this one first. Let's say first one. The result will be a vector. Do you agree? Then after that, you do this one, which is just equal to a matrix times a vector. Correct? And then finally, you do third. Agree? Agree? Now, this step is very obvious. This step is very obvious. Here's the important question. The first operation, you want to compute this, right? Can somebody suggest me what you should do? You want to do C inverse times D. Can somebody suggest me what is the best way to do? Should I take the inverse of the matrix C, and then after that I times the vector D? Is that a good way or is that a stupid way? That is a very stupid way. Because after you take my lecture, remember, never do the inverse of a matrix. You know why? Because usually in your real life application in engineering, the final goal is not to find out the inverse of a matrix, but usually after you find out the inverse of the matrix, you have to multiply with something else. Do you understand? In real life application, the final goal usually is not to find out the inverse of the matrix. Usually you want to find the inverse of the matrix first and then you multiply with something after that. So you keep that in mind, right? So now, of course, I know the matrix C. I want to find out C inverse times D. I will not take the inverse. But in that case, then how do I find out this product? Can somebody suggest me? What is a good way? It's not difficult.
Đầu tiên là mình lấy vector matrix C nhân với vector D trừ 1.
C times D à?
D trừ 1.
C times
D trừ 1.
D trừ 1.
Sau đó lấy trừ 1 của cả cái vector đấy.
That's not good, I tell you why. See, D is a vector. D is a vector. You cannot take the inverse of the vector. See, usually you can take the inverse of a matrix. Alright? Now, actually, some people, they can take the inverse of the vector too, but that belongs to a different method. In my textbook, I also describe about that, but usually, you can only take the, usually you only take the inverse of a matrix. So that's not a good idea. Can somebody else tell me a better idea how to get this thing? You want me to hear my answer? Okay, let me give you your answer, okay? C is a matrix, do you agree? So C inverse is also a matrix. You agree? And D is a vector. So C inverse is an n by n. Yes or no? C inverse is an n by n. D is a vector, n by 1. So the product will be a vector. Do you agree? So first you say, let C, this is very important, inverse times the vector D, define, let's say it's a vector Y. Understand? You define, give it a new name. Now, can you tell me what is your objective? You want to find out this product, right? Right? That That means you want to find out the vector y. Am I right? Yes or no? That means you want to find vector y. Well, the definition is C inverse times D with vector y, okay? Now let me see. From this system, can I multiply both sides by the matrix C? Yes or no? Yes or no? I can pre-multiply both sides by matrix C. Okay, now, what is C times C inverse? Identity. And therefore, on the left-hand side, all you have is just D. Do you agree? Because C times C inverse is identity. Now, how about the other guy? You have C times Y. C times Y. Correct? Remember, what did you tell me? You want to solve for Y. Is that right? You want to solve for Y because Y is equal to C inverse times D. Remember? C inverse times D is equal to Y. Remember? Remember? Your objective is to solve for Y. But look, your objective is to solve for Y. Can somebody suggest me what is the best way to solve for Y? I apply the Cholesky. You are right. Remember we saw Ax equal to B, we applied Cholesky. Remember? What does that mean? Step 1, you tried out the factorized matrix U from A. Remember? Step 2, forward. Step 3, backward. Remember that? This system is exactly equivalent to this system. They are equivalent. Do you know the matrix C? Yeah, it's given, right? So the matrix C plays the same role like the matrix A. And the vector D is also given, right? It is the same role like vector B. So to solve for the vector Y, what do? Step 1, I apply Cholesky. I say C equal to what? U transpose times U. Remember the Cholesky? Remember or not? Okay. Step 2. What is step 2? You do forward solution. Step 2, forward solution. Now what does that mean? In case you forgot, you replace C by U transpose U. U transpose U. Y is here. D is here. And then this product, you give it a new name. You call it vector V. Do you understand? This, you solve forward solution to obtain the vector V. And then step 3, what do? Backward solution. Backward solution. What does that mean? U, Y equal to V. U, Y equal to V. Okay? U, you know from step 1, factorization of the matrix C. Vector Y, you know it from vector V, you know it from step 2, forward solution. And from step 3 backward, you can solve for Y. That is exactly what you want. Remember, C inverse times the vector D is equal to Y. Do you understand? So from now on, please remember this very important statement. Never, never invert of a matrix. Whenever you have something like inverse of a matrix multiplied with some vector, that means it is equivalent like solving simultaneous equation. Do you understand? Okay. Now, let's say for the next 10-15 minutes, let me finish it off. So you understand this thing, right? So what is the thing that the most important thing that I have to explain to you? Do you remember? What is the most important thing that I have explained to you? How to obtain the precondition matrix P. Right? So far I talked about different things, right? But they eventually they will be related how to find out matrix P. Okay? Now, oh, can somebody help me to put back the conjugate gradient algorithm? Conjugate gradient algorithm. If you give me maybe 15 more minutes, and then I will help you to get the idea. Oh, okay. Oh, okay. So let's do a very simple one. Let's say you have Ax equal to B. You pre-multiply both sides by P inverse. Right? You pre-multiply. And then this one you call A star. This is X. And this one you call B star. So the $6 million question is P is equal to what? Now remember, I say P must be good quality. Good quality means what? It means P supposed to be very close to A. Or P inverse should be very close to A inverse. Now be careful, be careful. When I say P inverse must be very close to A inverse, what does that mean? Remember I say never take the inverse? I just say this in order to explain to you. But when I say P inverse must be very close to A inverse, what I mean is the factorization of P must be very similar to the factorization of A. That's what I mean. Remember I told you, right? Whenever you have an invert of a matrix, usually it means factorization and forward, backward. Okay. Number two, P must be cheap. Okay? So let me give you one example. I have three examples. Suppose I say if P is exactly equal to A. Suppose, remember we want to find out the matrix P, right? The precondition matrix P. If P is exactly equal to A, does it satisfy this criteria? Very good. You know why? Because if P equal to A, that means A star, by definition, equal to B inverse times A, which P equal to A means A inverse times A, it is equal to identity. Very good quality. Because the matrix A star will have the condition number equal to 1, remember? But, so if this is the case, right, this is very good news. But how about the second criteria? Is that cheap or not cheap? Not cheap, it is very expensive. So this is very bad news. Why? Because if you have to take the inverse of A, it means you have to factorize A. But if you factorize A, that means you go back to the Cholesky. Do you understand? So the point is this. If you look at the conjugate gradient algorithm, where is that? Ah, right here. Now, remember I already explained to you here. On the right hand side column, you know what we say? Conjugate gradient with precondition. What does that mean? That means on the right column, we're talking about solving the new system. Now, you can see they are very similar, except instead of solving Ax equal to B, now we are solving A star times X star, which is the same thing as Y, equal to B star. Do you agree? Now, what is the difference between, let's say, A and A star? Well, A star is equal to P inverse times A. Or, remember in the first method, you preserve the symmetry. Or, remember A star equal to P transpose AP. Remember? So you can see very clearly. Here we say, let's compute the so-called incomplete, this is the key word, incomplete Cholesky P. Now, right now, don't worry about it. I'll explain to you. Okay? Okay. Let's say you know how to calculate this guy. Assuming you know this guy. You see, very similar. Instead of B, now with PB. You remember? You remember this procedure? A star equal to this, and B star equal to PB. I talked to you earlier. Do you remember or not? Okay? So now, instead of B, it will be PB. Instead of A, it will be this. You see? You see that? Now, everything else do the same. Same. Except this step. Instead of A, it now will be A star. Do you see that? Okay? Everything is the same. Right? So what is the difference between the so-called conjugate gradient without precondition compared to conjugate gradient with precondition? The difference is that here you are solving the new system. Here you apply conjugate gradient to the original system. Okay? And in this algorithm, preconditioning, you need to know the matrix P. You agree? Now go back to this one. If you let P equal to this, then of course the matrix A star will be identity. Right? So what does that mean? How many iterations it will take to convert? One iteration. It will converge right away. Do you understand? Because when you say, what is that? P equal to A, right? That means you already use the Cholesky. You see right here? This guy B, right? If you say B equal to A, that means you have to find out, you go back to the Cholesky. And because of that, this loop, it will convert right away. Which means, essentially, you are solving using the Cholesky. That is one extreme. So, if you select P equal to A, quality is good, but it is not cheap because you have to factorize it. Now let me give you another situation. Suppose I say P equal to I, identity. So let me ask you this. If P equal to identity, P inverse, is that expensive or cheap? Expensive or cheap? Which one? If you say P equal to identity, it will be very cheap, right? So if P equal to identity, then that is cheap, so you are happy. But how about the quality? Good or bad? Very bad quality. Why? Because if P equal to identity, that means A star is the same thing as A. That means the condition number of your new matrix is the same, it's not improving. Do you understand? Now that means in this situation, if P equal to identity, then it is very cheap to get this guy. Very cheap. But it is not good quality. That means it will take you a lot of iteration. Do you understand so far? So right now you have two extremes. When you let P equal to identity, it is cheap, but it is not good quality. If you let P equal to A, what happens? It is expensive, but very good quality. Either extreme is not good. So what do you think is a good solution? Compromise. Somewhere in between. Do you understand? So, that means, well, what I want is I call compromise strategy.